CLion, a cross-platform IDE for C and C++. Download now.
Okay, hello everyone. My name is Roy, and today we'll talk a little bit about ranges. Hope you all had a very, very good time in the conference so far, and hopefully this next 60 minutes will be enlightening and um, exciting both for you as well as myself. So, as I mentioned, my name is Roi. It's actually pronounced Roi Barkan. I live in Tel Aviv in Israel. I've been doing C++ for quite a long time now, and for the last 30 years or so, I've been working for a company in Israel called Isra Research, where we do high-frequency trading, low-latency trading. Isra Research is always looking for good talent, mostly in Israel. And if you, I'll be happy to work with you and share experiences. And I'm actually also very, very happy to learn and explore new things around the language and around technology, like all across. So if you have any questions, anything that you want to mention during the talk, please use the Zoom Q&A feature. And after the talk, we'll meet in Gather Town as well. So let's get going and talk a little bit about ranges. So today, the focus of the talk is the ranges library. I'll try to introduce a little bit to so people will know what I'm talking about and give you a sense of my perspective as to what the strengths are, when we want to use it, and we'll go over the different types of range adapters, or also known as views, that are in the library. And then we'll also take a little bit of a step backwards and widen our horizon and perspective, and talk not just about the ranges library, but about libraries altogether, what they are, why people use libraries and write libraries, and try to think what the ranges library is good for and how it can be enhanced. And then we'll go looking for rabbits, which will be a large portion of the talk. And I'll give you some of my ideas, and then we'll see how it goes from there. So ranges. I personally think that the ranges library in the C++ standard is a breakthrough library. It's one of the big four features that were added in C++20, together with coroutines, concepts, and modules. And it was a long time coming, because a lot of C++ code had to do with algorithms and with things that could have used ranges, but they had to live without it. Even since 1998, STL was part of the C++ standard from day one, which had a lot of iterator-based algorithms. You probably all have heard of Alexander Stepanov, who's the main author of the C++98 standard template library, and the notion of ranges and concepts was already in his mind when we got the C++98 standard, but the language wasn't mature enough to have a ranges library, so we only had iterators. And then throughout the years, even before 1998, there was a lot of work in the computer science sphere related to vector processing algorithms, working on sequences of numbers, sequences of elements. There's a lot of theoretical work that's rooted in both functional languages and vectoric languages, such as APL, BQN, R, Julia, etc. You can hear a lot from Conor Hoekstra talking about these types of foundations that the ranges library was built upon. And even closer to home, various languages that are very similar to C++, such as D, Rust, and Java, they've also had the benefit of ranges and ranges-like libraries before C++20. And Barry Revzin also has a great talk where he compares all of those. And the C++ to some extent had the advantage of being like a late to the game. So C++ developers and maintainers had the advantage of being able to see all of this already unfolding and see the strengths and weaknesses of various approaches when they came in and they added ranges to the C++ library itself. So the main innovation, in my perspective, ranges compared to what we had before is the notion of composability. What do I mean by composability? So first of all, the input of most range algorithms is a range, and the output is also a range. This way, I can very easily pipe the output of one algorithm into another. This was very, very different, if you remember, what we had in C++98, where typically the inputs of algorithms were iterators, and the outputs were much less commonly defined. Like some of the algorithms, they did in-place changes to their inputs. Others had to accept an extra argument, which was like an output iterator. But again, it was like an extra argument that was passed in as an input and behaved like an output of the algorithm, which isn't as composable as chaining functions one into another. The second term, which I think is the strongest in terms of composability, with ranges, is the notion of range adapters. Range adapters are basically sort of like encapsulating full range algorithms into what's looks like another range or lazy range. These are also called views, and we'll dig deeper into them throughout this talk and learn what they are and why they're so strong when it comes to composition. And again, when we use the range adapters, the whole line between what is an algorithm and what is an object blurs. And this is also something that's pretty common in the functional programming kind of languages. And this notion of having objects that are variables on one hand and algorithms on the other can sometimes be very, very powerful. We'll see some examples later on. And the third notion where composability comes in the ranges library is this new concept called projections. And projections are these small ways to tweak or alter the behavior of certain ranges, algorithms, adapters, etc., in order to better fit the inputs to the outputs. But if we have some operations that we want to do, which doesn't exactly fit the inputs that we want to work with, etc. Sometimes projections give us those ways to make like certain small tweaks in order to really compose what we want without needing to get out of the ranges world and back in. So let's dive deeper into what composability means. So as I mentioned, the input and output of range algorithms is now not iterators, but ranges themselves. This means that I can use the search algorithm, for example, and the reverse algorithm and compose them very easily, like any other like functions that exist in C or C++. So in this example, I could take a string, I can look for the substring ABC. The search algorithm will receive those as inputs, return them as an output, and then reverse can take that directly, reverse those ABCs into CBA, and it all fits very, very nicely. I don't need to muck around with where the information lives in memory, the whole in-place iterators kind of things. It all, I don't need to deal with that so much. It all just really fits in together nicely. Views and range adapters. Again, this is like it's one of the key tenets of the ranges library is this pipe operator, where this one single line, I can basically take a string as an input, split it by spaces into the different words, and then take the first two words. So basically very, very expressive. I don't need to tell the compiler or whoever reads my code too much about how the code is actually running and what's it going to do. I'm just more expressing what I want it to do. Okay, so I just want to take a string, split it into by space into words, take the first two words. Very, very simple, very, very easy. And this ease of use makes it so that even we can take these algorithms, take these range adapters and create our own vocabulary, our own dictionary of algorithms that we can use, even if they're not part of the standard library. So in this example here, I'm taking two words of the C++20 dictionary, the filter and transform range adapters, where filter basically is the term used to take a range of elements and just pick specific ones out of them, the ones that match some predicate. And transform takes, again, takes a range and performs some operation on each and every item. And here I have my own new word that I can use inside my code base, square event, which is the composition of a filter and a transform with specific lambda arguments. So I can get this duality, as mentioned, of this algorithm that I have, which is also just a variable that I can use. And if we look closely, we'll see that this first pipe in the second bullet here is a pipe that its first element, its leftmost element, is a range on its own. And if a pipe expression starts with a range, then the entire expression basically behaves like a range. It's a lazy range. It doesn't. There's no memory allocation taking place here, but I can use this expression as something that I can iterate through, etc. If I have a pipe expression like the third bullet here, where the first element is not a range, it's just an adapter, then the entire thing behaves like an adapter. So square evens is not something that behaves like a range. I cannot iterate it myself. It's just something that behaves like an adapter. And I can tack it on other types as I work along, as I work along, as I write my code. And I basically have a richer dictionary, a richer vocabulary of how to work with things. So I don't have to build the entire dictionary myself. Happily, C++ gave us a very, very rich terminology and very, very rich language to work with. This actually is not even the full list, but there, as you can see, there are many, many views or range adapters that can be used that already come out of the box. In this list here, I mentioned all the important ones, in my opinion, both coming in from cplusplus20 through cplusplus26. Everything has already been voted in. And we'll try to go over them one by one so you get a feel of what they are. In order to try to make sense of all of it, I try to break them into different categories based on the ranks of their inputs and outputs. So let's talk a little bit about what I mean when I say rank. And rank is sort of like the dimension of a range. Basically, a range is a sequence of objects, right? So I can have a sequence of integers, a sequence of doubles, a sequence of strings, et cetera, But sometimes you go into a higher dimension. So we can have a sequence of sequences. And some of the algorithms, they basically change the rank of their inputs. They can, for example, take a sequence of sequences as an input and return something that's just a flat sequence of items. So this is what I call a rank changing adapters. And in C++, unlike other languages, it's not the matter of ranks doesn't only describe or has to do with the dimension itself, but also with the fact that sometimes you can increase the dimension either through a runtime mechanism or through a compile time mechanism. So we have this compile time mechanism of creating extra dimension using a std tuple, for example. Okay, so tuples are an extra dimension that is known at compile time, whereas a range of its own is something that's only known in compile time. So, for example, a range of strings can be considered as like a range of ranges of characters, whereas a range of tuples, where each tuple is 3 characters, is also like a rank 2 type of object, but each of the element its dimension is known at compile time. And as you can see, most of the adapters that we already have in C++ 20 and through 26 are those rank preserving ones. They take ranges in one specific shape, and they return potentially a very different range, but of the same shape. And just to be precise, I already mentioned the filter adapter. The filter adapter, typically the output is smaller than the input, but the shape is the same. Okay, the number of dimensions in the input of the filter is the same number of dimensions as in the output. Just the number of elements in each dimension might be smaller. Okay, so let's go over some examples. So again, we'll start with the factories or generators. Those are range views that don't take any range as an input. They just take something else and they create a range. Okay, so the empty range is a way to just create an empty range. You can create very easily ranges of sequences of a single element or ever increasing ones. And then we also have this repeat construct where we can just take a single element and repeat it multiple times. Okay, I should also note that the ranges library also supports infinite ranges. And that's also something really cool that sometimes can be helpful. Okay, moving on to rank preserving range adapters. As mentioned, there are many of them in the library. So let's look at a few examples. So again, the simplest one is std : views : all. And basically, the all adapter just spits out as the output exactly what was in the input. It seems like something that's redundant, but sometimes it can be very helpful. And it's sort of like a generic way to make sure that anything can be converted into a range. And here we have like the iota range that looks at all the numbers from 2 to 10 without the 10, and piping it into the all view basically doesn't change any of it. If we go and try to use a filter, we'll give it with a predicate that basically returns not 5. We filtered out the number 5. Transform, as you've seen before, can perform a transformation on each and every element one by one. And take and drop are other adapters that basically manipulate the head or the tail of a range. Just take the first few elements or drop the first few elements, and all of these together, you can see they're they sometimes can fit pretty well together. Okay, next up. We have some more rank preserving ones. We have take while, which is very similar to take, but it works with a predicate. So it's sort of like a combination of take while and the filter thing. What it basically just takes the prefix of whatever range we give it until we get something that's where the predicate returns false. Drop while, very, very similar, just gives us the tail. And then there's the reverse adapter, which can get any range that's, I think, bidirectional as its input, and they can just reverse it, which is cool. And then there's a stride and adjacent transform, which also gives various ways to receive a shape in one hand and work and gets some manipulation on the results. You see that adjacent transform, by the way, it's templated on the number of adjacent elements that can be used. So basically, adjacent transforms, you can see it sort of like looks at like a sliding window of its input and performs whatever lambda operation is given on each of those windows to generate a result out of it. And specifically here, you can see that because adjacent transform is created with a template argument of 2, the output of this adjacent transform is the same shape as its input, but with one fewer elements, because I needed a pair of adjacent elements to create in the input to create a single element in the output. Okay, cool. And then cplusplus 26 gave us very, very recently was voted in one other rank preserving adapter called cache latest. Cache latest is actually similar to stood colon views colon all in that it doesn't really change the functional behavior of whichever range it adapts to, but it gives different performance characteristics. So cache latest basically tries to not to avoid recalculating or recalling the star operator on its input, and basically stores whatever the last item or the latest item that it needed to return or calculate, stores it in memory in order to avoid extra calculations. Okay, so those are the rank preserving ones. Moving on to the variadic to tuple types of adapters. So again, the most common one that people who are familiar with Python probably know is the zip view, where basically we take a variadic number of ranges in the input and we generate something of the same shape, but just a single range of tuples, where the number of elements in each tuple is exactly the number of variadic arguments that zip received. Okay, and very, very similar in shape, but much more complex and longer in nature is the Cartesian product, where again we take a variadic number of ranges in the input and create a range of tuples as output. But these tuples are basically each and every one of the potential combinations. Cool. Let's go and look at these adapters that decrease their rank. So they can take a tuple as an input, like or a range of tuples, sort of like a zip. And if we take the colon keys, the std colon views colon keys, that's basically a shortcut to just taking the first item in each of the tuples. So this like assumes that this range of tuples that we get as an input is sort of like a tuples where the first element is like a key and the second element is like a value. And this is like it really lends itself well to piping these views into like a map or an unordered map, where this is basically the way things behave. But you can tack std v colon keys and views and values to any input range that has tuples in it. And then the generalization is std colon views colon elements, where there's like a compile time known template argument which specifies which of the items in each of the tuples need to be extracted out. Okay, so those are our range decreasing adapters that work on ranges of tuples. Similarly, we have some range decreasing ones that work on a variadic notion, and That's a zip transform, for example. So again, you can take a different number of items of ranges as variadic pack in the input, and one lambda, and we'll transform each and every item, or each and every, like consecutive or matching pair or triplet of items into a single element, and that way we'll reduce the rank from a variadic number of ranges, all of the same length, into one single range, just using this transformation operation. And if, by the way, the different variadic ranges have different length, then zip transform will just return the a range that's the shortest of all of them. So it takes just the minimal length of all of them. And then stood colon views colon concat. It also converts a variadic range into a single one, but basically by just concatenating them. Okay, so I have the numbers 2 through 6, and then 6 through 9. I can concatenate them, and I get the entire range. Okay. Then we have the range decreasing versions based on ranges of ranges and not ranges of tuples. So stood views colon join is the typical one. I can get several ranges and just concatenating them into a single one. So here I took 2 string views and converted into one flat range of characters. And then there's join with to add a delimiter. These are probably very, very known to people, again, who are used to Python. And if we go from the range decreasing family to the range increasing ones, again, stood views enumerate should be very, very common to those versed in Python, where we basically just tack on an index of an item to each and every item and get this sort of enumeration. Later on, we can tack on these things like stood views keys or values, as we see before, to get whatever index we like out of those tuples. And then there's also stood views adjacent, which create these sliding windows, basically of tuples of length or size that's known at compile time. And then the increasing adapter family that doesn't work with compile time tuples, but with runtime ranges, where the size is not known to compile time, are split, which basically takes an element and at compile time just try to look for that element and split items based on it. We also saw an example of that a little earlier on. And lazy split is very, very similar, but has a slightly different runtime behavior when it comes to how many passes it needs to go on the input and whether input needs to be like a forward range or an input range, etc. But the basic behavior is very, very similar. And then there's slide, which is has the same shape, but instead of splitting items, it basically creates sliding windows. As you can see, slide with number 3 is similar in nature to adjacent, templated on 3, but with the slide example, the number or the size of each window is known at runtime, and whereas with adjacent, it needs to be known at compile time. And then the chunk is again very, very similar to slide, but instead of getting sliding windows, basically just chops off every nth element, very, very similar to stride. Or no, it's not similar to stride. It's similar to, I don't know if there's a parallel in the tuple world. And then the chunk by is a similar notion as chunk, but instead of looking for specific windows of the exact same size each, chunk by will basically look for adjacent elements and try to see if they match some sort of predicate. And in this case, we're using equal to. So whenever various adjacent items are equal to each other, they'll be chunked into the same sub-range. Whereas whenever we see a pair of different of adjacent elements that are not equal to each other, that's an indication for chunk by to create a new sub-range. And basically this way we cut a range of characters into several ranges of ranges, each of them of identical characters on their own, and we've increased the rank. Okay, great. So basically we've gone over many ranges of range adapters in a very, very short period. This is again a recap. And the thing is that these are now new words in our vocabulary that we can use as we write our code base. Some of you know that their code base is still on C++20, and moving towards C++ 23 and 26, I can say that some SDL implementations are not fully compliant yet, and although they claim to be C++ 23, they might not have all the different adapters for C++ 23, but definitely these all are, have been standardized or are in the pipe. You should learn them and know how to use them. And if you want them in your code base, there are typically other ways of getting them as well, even if your current compiler and current SDL does not support them. And by the way, this last bullet here, you can use it to try and get a peek or sneak peek into the plan for the committee of adapters to try and add for C++ 26 and to the future. Okay, so again, if you have any questions on range adapters and how they work, feel free to use the Q&A feature in Zoom, and let's move forward to our second section, where we zoom out a little bit, widen our perspective, and talk not just about the ranges library, but about libraries in general and what they are. Okay, so what is a library? Why do we take a piece of code and call it a library? So obviously there are a lot of definitions, and many people can think of it in many ways. The first thing that came to mind when I asked myself this question was that library is code for coders, compared to code that we write for some other people who just want to use the code, and they come from other professions. If I write code, my main user, my main target audience is other people who write code, I think of it as something that is a library. Another notion or another answer that you might think of when you ask yourself this question is that a library is something that's self-contained and reusable, a piece of software that you can just wrap it up inside like a container or a zip file or wherever, and just ship it or give it to some to different pieces of software, and they can be reused over and over again in different circumstances. Another notion that comes to mind when talking about libraries is the notion of abstraction layers. Abstraction is basically trying to think of the different tasks and the different objectives that our code wants to achieve in different depth of understanding, and trying to see if we can somehow manage to make this very, very large complex system into something more manageable by basically breaking it up into layers. So libraries are supposed to be a mechanism to help us with abstracting things. So we'll see a little bit more about that in the next few slides. Another potential answer to this question is that a library can sometimes be a language within a language, sometimes called domain-specific language, right? So, for example, regular expressions are sometimes considered like a language that's within, like a regular expressions library is a language within C++ or a language within Python or Perl, etc., etc. And good libraries, they sometimes can seem to be like an embedded language, and a foreigner that doesn't know that library will look at our code and might not really understand what's going on. But once they get a sense of it, they really become fluent, similar to the way that they are fluent with the external C++ or general purpose language, whatever it is. And then the next way to think of libraries is sort of like a Lego blocks or building blocks, where you can basically create these different components within a library and hook them up or compose them one with each other. And when I asked people, or when people think themselves, what is a good library, not just what is a library, I think one of the main questions or concerns that people think about is what's known as the interface, or the API, the application programmer's interface, the way that the inside and the outside of a library interact with each other. And this is something that's sometimes, if you want to get a good library right, you think about that quite a lot. And lastly, I guess, when people think about a library, not even in the programming language term, they think about words, they think about concepts, they think about vocabulary, about these new terms that once they are aware of, they just enter their language and they can start working with them just like any other thing. Okay, so that's what I think about when I think what a library is and what the ranges library is. I think each of the bullets in the slide is answered perfectly by the C++ ranges library. I think in many aspects, whatever's going on in ranges library, checks every bullet here, and so in that perspective, the ranges library is a really good one. And if we try and learn from that, maybe we can get our code in better shape. So to give us a little bit more of an insight about the importance of writing libraries and writing them in a good way, here's a short clip from 1984. It's a long time. I assume some of you were not even born yet, where Hal Abelson, one of the authors of the SICP, the Structure and Interpretation of Computer Programming book, basically describes his idea and the importance in his mind of writing libraries. So let's hear a few words from Hal Abelson.
But the important thing is that between these and these, we set up an abstraction barrier. We set up a layer of abstraction And what was that layer of abstraction? That layer of abstraction was precisely the constructor and the selectors. Like this layer was makerat and numer and denom. Okay. This methodology, another way to say what it's doing is that we are separating the way something is used, separating the use of data objects from the representation of data objects.
Okay, so we're separating the use of a data object from its representation. I think many of you have heard these types of things before. We're talking about libraries, we're talking about object-oriented programming, etc. And you can see that this is hardly a new idea, but this is an idea and a concept that really stood the test of time. And writing our own code hopefully will stand the test of time if it also meets this criteria. So in that sense, I claim that libraries and writing libraries is something that we should do. It's not only the act that people in academia or people in the standards committee do. This is something we should do on our own, and we should be able to write our own libraries on top of the existing libraries as much as possible. So why do I think that's the case, and why do I want to advocate that you approach your own day-to-day tasks at work or when you code even for fun in a library kind of perspective and point of view? First of all, for the reuse perspective, we all know that we want to try and not repeat ourselves. And as long as whenever we write a piece of code and we don't just think about our immediate use for it, but maybe of potential other future uses, we try to write something that's more reusable, then there's a smaller chance that we'll need to rewrite something very, very similar in the future. We won't need to repeat ourselves, which is really cool. Another reason to write and to consider our own code as a library is to think about vocabulary. Okay, not just write our code in order to create a task, but also write some code in order to enrich our discussion, to be able to talk in a different level, in a higher level, with our colleagues, with our managers, with maybe even our customers. If we create very, very good verbs and nouns inside our code base that later become shared with our customers, with our peers, etc., the level of discussion becomes higher, and we sometimes can really reach more profound understanding of what it is that we're trying to achieve whenever we're writing code or whenever we're shipping a product. And then the notion of building blocks, of really separating our entire code base, our entire project into several sub-libraries can really help, because it can help us think about the layers and the depth in which each building block resides. So the higher we go, the higher whatever we consider like a high-level piece of language or a high-level library is something that's typically closer to the customers, closer to the actual users. And those are pieces of code where change is typically more likely. Okay, those are pieces that typically be harder to solidify, because the customers will always have newer and newer requirements and always have different requirements. Whereas when we go lower, we can reach a much stronger level of stability and much have a potential to be much more robust. And many times it goes hand in hand with the fact that the complex code is typically one that can go to those lower, more stable levels. So if I manage to make my code such that all the complexity or most of the complexity lies within those pieces of code that I know are low-level libraries that are more stable, more robust, don't change on a whim because some customer wants something else, then I know that it's safely encapsulated. I know that this complexity, there's little chance of getting it to break once I know that it works. And again, if it's in a low level, it's typically better defined, so it's easier for me to write the preconditions and post conditions for it. It's easier for me to write tests for it and make sure that whatever's in the low level, it's typically code that it's higher for me to ascertain is correct and it works well. So ideally, I can put the complexity in there and hide it away from all those higher levels where things are more likely to change, more will be harder to test, to validate, etc. So as mentioned, this way of thinking of our code as libraries and as of layers will typically get us to a way or to a place where we know that most of the complex stuff is in a place where we can manage it better. And most of the code that is in flux is not too complex, is simpler, it's easier to reason about even just by inspection. And then, as mentioned, libraries is not just like a two-pronged approach. It's not a dichotomy that each piece of code is either library or an application code. These things are totally can be stacked on one on top of each other. So at the very, very lowest level, there's maybe the operating system or like the POSIX APIs. Then on top of that, you can think of a languages standard library such as the STL, etc. Then you can think of other libraries like which are written by someone else, like Qt, for example. And then even within our own code base, we can stack things up and layer them sort of like with turtles all the way down. Okay. And this approach, hope like happily, it's not only something that I've been thinking about. This is a slide that I stole from presentation by Sean Parent about software safety and security, where he also has a vision where all of our code base or all good code base will basically be just some composition of many generic components that are highly generic, highly proven, highly testable, and then composing them into application is so easy and so trivial that it can even be done using a non-Turing complete declaration form. So all the complex stuff, all the things that really need the Turing completeness will be in a library, and everything else is just building puzzle pieces. You're very welcome, by the way, to click the link on your own spare time and see Sean's great talk, where there's this slide itself also has a third bullet, but I won't spoil the surprise of what his third bullet for the future entails. So hopefully I convinced you by now that ranges library is a good one, and that we should also write our own libraries or extend existing ones. And in the rest of the talk, I want to try and write my own extensions or suggest my own extensions to the ranges library. As we mentioned, more ranges, please. And let's try to think about how should one approach this task? How should one start by writing a new library? Okay, so there are many talks online from people like Chris DiBella and Eric Niebler, basically telling us that we should start with the algorithm, start with a problem and a potential solution of how we think this problem can be solved or can be approached. We start with having a specific recipe for a solution or some code that we want to maybe convert or make into the heart of our library, and then we'll just write whatever we need for day one, and then we can go through this iterative process of generalizing it, distilling it, simplifying it from where we started with something that's very application specific into something that's very generic and general that can be used in many places, can be tested, etc. And typically, as we distill our code, what will emerge, what we'll understand is what are the generic things that our algorithm really expects from its inputs and really provide on its outputs. And these typically can become C++ concepts. Okay, so a concept typically is something that we will learn about our algorithm as we distill it and as we simplify it, we'll understand what are the exact requirements that we have from our inputs, etc. And then, as I mentioned before, we want to pay a lot of attention to the API itself, the abstraction there between what's inside the library and what's out of it. And again, there's a great talk by Ben Dean and others. There's also, I think, Scott Myers really like talking about the fact that we would like our APIs to be easy to use and hard to misuse, to get the language and the compiler, to be on our side as much as possible, and to make it so people will not need to read too much documentation to understand what's going on and how our library is meant to be used. And we'll want to consider preconditions and postposition. C++26 will have this potentially as part of the language with contracts, but even before C++26, whenever we write a library, we should really consider and think hard about what the preconditions and postconditions are for whatever algorithm, whatever libraries you write. And then Alexander Stepanov, the author of STL, he also coined the law of useful return, where it basically says that whatever non-trivial piece of information that you calculate within the within your library should be exposed or should be available to whoever called it, because potentially they might want this extra non-trivial piece of information. Another rule of thumb is to try and aim for data types that are regular or algebraic. This is something that's known from the functional languages type of world. And again, Stepanov also discussed that a lot. And the notion of value semantics, where we talk about values and not the object, that sits very well with the legacy of the C language, etc. And I really, as we write our objects and our libraries to work with value types, there's less of a chance of people not understanding what they're expected to do and what they expect our library to, how they expect our library to behave. And if there are any algebraic notions that we can think about that relate to our data types, like is this an algebraic group or a monoid? Are we working with monads? That's also something that sometimes, if we figure it out, or if we realize that an algorithm or a library that we're working on actually has this type of algebraic behavior, it can really guide us in a better way in understanding how we want people to use it, and now that people might want to use our code in the future in other scenarios, and whether it will make sense for them or for us to make sure that that we convey our requirements to our users in a way that is solid enough in a mathematical level. Okay, so we know if we have an idea, we'll start with an algorithm. How do we find the algorithm? Okay, how do we start? And the basic premise is that we don't have to look very far away. There are many places where we can, we are given tasks at work. We look at other talks on YouTube about C++. We see various people writing and implementing various algorithms. Sometimes you see them implementing other programming languages. Sometimes you see them as just a single part of some existing library, and we can go and find them and understand that there's a library of its own in them. And again, let's look at Alexander Stepanov, the author of STL, talking a little bit about this notion of how to be a scientist, how to create libraries from scratch. Let's hear what Stepanov has to say.
Unfortunately, in 20th century, there is a very wrong idea of science developed in popular culture. And Einstein, who was, of course, a great scientist, is partially responsible for that. The idea is that scientist is somebody who has long hair, never gets a haircut, seldom washes, and discovers some wonderful, wonderful things because of some inspiring breakthroughs. And science is actually, it's something you do on a regular basis. I think a much better paradigm for a scientist is somebody like Carl Linnaeus, who established modern zoology, which is you send your disciples all over the world to bring you examples of animals and other living species, and then you try methodically to classify them. Science is about classification. Science is not about grand inspirations.
Okay, so science is about classification. It's not about grand inspirations. We see examples of code, we see examples of problems in the world. We suddenly realize that, hey, there's something that's repeating, recurring, and maybe we can create a library out of that. Maybe we can create an algorithm out of that. Maybe we can create a range adapter out of that. That's what Stepanov tells us here. And let's hear one more short snippet from that same talk by Stepanov to really try to drive the point home.
I have to meet occasionally with people who are doing so-called research in computer science. They say, well, I don't know, I don't have any ideas. Don't have to have any ideas. Go catch rabbits. Go look at people's code. Go find what they do and try to abstract it.
Okay, so Stepanov basically is asking us and everyone in the audience to go and catch rabbits. If we want to really try and create good quality code, create libraries, we don't have to work that hard. Just look around, open our eyes, look at rabbits, go and catch some rabbits. And this is what we'll do with the last 15 minutes that we have, and try to find some rabbits on our own in the ranges space. Okay, so the first rabbit I came to mind for me when I saw Tina Ulbricht's talk on C++ on C. I think it was 2022 maybe, where she basically told people how to take non-range code and write them in a range manner. And one of her examples was this very, very tricky algorithm called the Hond method, which is meant to assign seats in a parliament based on a party voting democracy. So here's the method in a few words. Basically, we have, again, some parliament. We want to assign seats into it. People are voting into one of three parties. And in this example, party number 1 received 110 votes, party number 2 received 85 votes, and party number 3 received 35 votes. And the Hond method basically said, so we create this table with one column for every party, and in each cell in the table, we'll write in the number of votes divided by the row number. So for party number 1, all the items will be the number of votes divided by ever increasing numbers. Party number 2, again, the number of votes ever increasing divisor. And same party number 3, and then the Hond method basically said that all you need to do is just sort these numbers in the cells and pick into your parliament the seats based on from the highest to the lowest. So the highest number here is 110. So the first seat will go to party number 1. The second seat will go to party number 2. Third seat will go back to party number 1 because 55 is higher than 42.5. Fourth seat will go to party number 2. Fifth seat to party number 1. Sixth seat will go to party number 3, and then the seventh seat will go to party number 2. And that's the Hond method. And Tina Ulbricht in her talk basically showed how this algorithm can be implemented with and without the ranges algorithms. And she showed how using ranges can make things much, much simpler than before, but still it wasn't as elegant as I hoped it would be. And basically, let's see how she tackled it now. This algorithm can be tackled using C++ 20 ranges. And the heart of it was this call to stood : ranges : sort algorithm. Basically, after she created this table of cells, this sort operation could be used to basically sort things from highest to lowest. And then there was a call to resize, to basically take only the first number of seats as we need, and drop like all this lower right region of the table. And this was a really, really cool talk. And as I was on the train back from Folkestone, I thought about that a lot, and the fact that I really didn't like this resize operation here, because I figured that we're doing all this work during the sort operation, and then with resize, we're dropping a lot of the results. Okay, so a lot of work is being spent sorting all this table, sorry, but then we're dropping all of the results. So I thought that this could be improved. And so basically, the sort operation is eager, and it takes S times P cells. S is the number of seats, P is the number of parties. And then with the resize, we're throwing a lot. And so first, the first, I guess, idea that I had is that STL itself has a better algorithm called nth element. And I can use nth element to basically not sort all of the S times P cells. I only need to find whoever is the nth element, the element number 7 or the element number S, and partition the results such that the first or the top n ones are at the start of the range, and the least ones are at the end of the range, and then I could resize and do much, much less work. And the second insight that I had is that even nth element doesn't have any requirement, any precondition on its input, either that it's just size of S times P, or it just takes any input and converts and finds the nth element out of it. And actually, with the hunt method and with this algorithm, we know a little more about our input. We know a little bit more about our preconditions. We know that each and every one of the columns here is already sorted, right? You know that all the items in the column number 1 are decreasing in nature, and the same for each of the columns. So basically, all we need to do is not find an element without knowing anything about the input. We know that we can actually use the merge algorithm. Okay, and merge is something that's already existing to some extent in C++98, and it's used to basically take several, 2 or more ranges that are already sorted and merge them into one consecutive items that are sorted across them. And the complexity here can go down much more dramatically from S times P to S times log P, which is really cool. And if people recall or know from bachelor's degree computer science, this is something that's typically done using a heap or a priority queue data structure. And an extra point that I thought about is that this merge operation is lazy in nature. Okay, I don't need to have the entire S times P or even items in memory. All I need is just the top item from each of the columns available to me, and then I can basically walk step by step, find the top one out of each columns, output that, replace it in the heap with the next one, etc., etc. So I can do this merge operation in a lazy fashion. A lazy fashion is certainly not a range algorithm; it's a range adapter. Range adapters is one of the key tenets of the ranges library, which I think is pretty cool. And that's our rabbit number 1, trying to create new stood views or stood ranges views for sorted ranges, not that know that their inputs can be sorted. So basically, we can create a view for that merges its inputs, it creates a set union, a set intersection, and symmetric difference. All of these names, they're not my invention. All of them already exist in the iterator version of C++98, but they don't have corresponding views. And another thing to note is that typically you could not only merge or take the union of 2 different input ranges. You can take a variadic pack or a multiple number of inputs and work with them and get a better performance using, again, like a heap or a priority queue structure. And so, as mentioned, STL since 1998 already had these algorithms, but not as range adapters, and only working with 2 inputs at a time. And obviously, there are other algorithms in C++98 and onwards that accepted or worked on sorted inputs. Okay, it's not very clear how those algorithms can be turned into range adapters, but potentially they can be. So there's a lot of thought already in STL about writing different algorithms where the input is already sorted, but there are still no range adapters or views who expect those inputs to be sorted. And again, all of the operations are lazy in nature. Looking a little bit to widen the scope and to make sure that we're not inventing something out of thin air, I looked around and I found that the ranges v3 library that the STL ranges library was basically based on did have or does have views for set union, intersection, and symmetric difference, which is really cool. It only supports 2 input ranges and not a variadic number, and there's no merge operation. But it's a good step in a good direction. It gives me motivation to maybe write my own merge and put it maybe in range v3. And then the D language itself also has the merge and multi-way merge operation working on sorted inputs. The difference, by the way, between the 2 is that one is variadic in nature and the other is one that works on ranges of ranges. So both these operations, they are decreasing rank. One takes I guess a variadic number of sorted ranges, and the other takes just a range of ranges where each of them is sorted and results in the merge. Okay, so that's our rabbit number 1. And let's we have a little more time, so let's talk a little bit about a few more rabbits. So let's think more about these notion of sorted ranges and what we can do with them. There's, again, we have these algorithms that work pretty much or can work maybe in either logarithmic time or close to logarithmic time called equal range and unique, and they can also basically be used. Right now they're algorithms, but those have the right signature, they have the right lazy kind of work in them, where you can make them into pipeable things, and people can use them to get from the first to the last items in an equal range, in a lazy fashion, without needing to do a lot of work up front. And the entire notion of binary search, if our inputs are sorted, can become these types of filtering views for random access ranges. For example, we saw that we have take and take while and drop while. So potentially we can implement range adapters called take until and drop until, which will basically behave very, very similar to take and drop, but can be faster in terms of runtime, in terms of runtime complexity, because they know that the input is already sorted. And technically, take until only needs it needs to have its input as random access. Then we can also implement the take between. And as Chris DiBella told us, now that we have a large set of algorithms who expect their input to be sorted, we can start distilling those and think about new concepts. And potentially we can think that maybe our library can have a new concept called sorted range. And a sorted range is something that's sort of like a range that's maybe it's a forward range, maybe even random access, and we can know what its comparator is, etc. And if our language has this concept, we can write our adapters in our code in a way where the compiler helps us and make sure that we will not pass something that is not sorted into those algorithms by mistake. And the D language has this type of concept and has these mechanisms called is sorted and assume sorted that basically take ranges that are not known to be sorted and converge them into ranges that are sorted in either by checking at runtime or just by assuming that that's the case. And again, once we have these things, and we know that things can be sorted, we can very, very easily also add the words to our vocabulary. So for example, the word histogram is something that can be very, very easily implemented if I know that a range that we receive as an input is actually sorted. All I need to do is just basically chunk it by equal items, and then I can convert each of the chunks into just a single element, which is like the representation of that chunk, and it's the size of that chunk. Okay, hopefully that all makes sense. So that's our rabbit number 2.
When I just go catch rabbits.
Okay, we caught another rabbit. Don't have a lot of time, so I'll skip this regression and talk a little bit about ways towards rabbit number 3, where we basically try to break the sort operation apart. This is inspired by some, categorization that I did through looking at the R language, where the sort operation basically does n log n operations, but it actually performs 2 different n log n operations. First, it performs n log n comparisons, but it also performs n log n swaps. And sometimes a swap can be much, much more expensive than the comparison. And an example can be where it has to do with even with projections. Because when we use projections, we sometimes want to sort very, very large items based on a very, very cheap comparison of just one of the aspects of the items that we are sorting. And once we know that swaps are expensive, maybe we can have a better sort that does n log n comparisons, but fewer swaps. Maybe we can do only n swaps. And the basic idea is that we can do it if we break the sort into 2 different operations. One is an order operation that basically doesn't really swap anything around. It just takes a range as an input, and it generates the order or the permutation as a result. And if I have that permutation at hand, then I can go over and perform just a single pass of reordering or swapping things just once using that permutation. And moving even deeper, you can think of the implementation of this order function very, very easily using iota and some projections. So this is our rabbit number 3, trying to think of permutations as, again, like a new concept inside our library. And a permutation is something that it can be reversed. It's sort of like an algebraic kind of thing. There's applying permutations one on top of another is something that can be done, and it's very, very easy. We can apply permutations on information using a lazy approach, without actually swapping anything around. And this is actually something that exists both in the Boost library and the Thrust library. And again, our libraries can go and use it. I'm running out of time a little bit, but again, there are also already algorithms inside the STL that deal with permutations, and potentially, again, we can create our own concepts that define information as a permutation or as a permutation of some specific range. So
I just go catch rabbits.
So that's our rabbit, potential rabbit number 3, trying to enhance our library with this notion of a permutation and trying to create these adapters and operations that work not only on pieces of information, but on permutations of those pieces. So let's sum it all up and say that, again, the cplusplus ranges is an exemplar of composability from my point of view. And libraries in general can make our software better, clearer and cleaner, and potentially it's all around us. We don't have to wait for someone else to give us libraries, and we don't have to look at GitHub. We can also have ideas, write our own libraries, publish them, contribute them, and work with them. Even the cplusplus ranges library itself can be improved and enhanced. So please, everyone, I hope you had a good time and learned a little bit, and go catch rabbits. Thank you very much.